In Chapter 18, we mentioned that if we took 1 kilogram of water and raised the temperature by 1 Celsius degree, this required an energy of 4,186 joules. We said that very casually, but when you think about it, that's a very large amount of energy. If all of that energy were in, say, the kinetic energy of the block, how fast would it be going? Well, let's take a look. Kinetic energy equals 1/2 mv squared. V is the square root of 2k over m. So that's the square root of 2 times 4,186 kilogram meters squared per second squared, divided by 1 kilogram. Pulling up a calculator, (1,186) times 2, take the square root, 91 meters per second, or almost 200 miles per hour. Evidently, there is a lot of energy stored just inside the material based on its temperature. That really raised a lot of questions. Why would there be so much energy? And the suggestion was that there are actually little particles, atoms, and molecules and these small objects are moving around very fast. And when they heat up, they move faster. But the question is, how do we model those? It's obviously a tremendous amount of energy, but we would like something simple to model them. Liquids and solids are actually quite challenging, but how about gases? The key thing about a gas is that given how easily it can be compressed and how it's very fluid, we would think that gas molecules are actually very far apart compared to their size, so we can easily press them together, and there's relatively little force between them. So maybe we could make a model where we just imagine these particles moving freely in perpetual motion without ever slowing down. And maybe that model could give us realistic results. So we'll explore a model like that. But before we do that, let's take a look at the macroscopic behavior of gases.